1 2 check check. We're back. All right, cool. So, hopping into this object-oriented programming quiz, we can access inherited methods that have otherwise been overridden by using which built-in function? We can access inherited methods that have otherwise been overridden by using super. In Python, we can customize operators like plus for arbitrary objects by overriding the add dunder method in that object's class definition. In Python, how do we indicate that access to a class member should be considered protected? In Python, we indicate that access to a class member should be considered protected by prefixing the class member with a single underscore. We start a variable or method name with a single underscore to indicate it should be considered protected. In Python, which class should we inherit from to create an abstract class? ABC, where the abstract base class is used to indicate a class is abstract. In Python, how do we indicate that a class member should be considered private? By prefixing the class member with two underscores. We start a variable or method name with two underscores to indicate it should be considered private. Which of the following is achieved by using setters, getters, and deleters to access and write to private or protected attributes? Which of the following is achieved by using setters, getters, and deleters to access and write to private or protected attributes? I believe this is abstraction, encapsulation. Abstract classes tend not to have getters and setters, while the implementing classes do. The four pillars of object-oriented programming that Python supports are inheritance, abstraction, polymorphism, and encapsulation. 85. Honestly, I usually skip these, and I will skip this one as well, just because I have to keep the goal in mind. I'm trying to breeze through these, honestly, to get to the data structures and algorithm study. So, the at property decorator. Learn about the most Pythonic way of using getters, setters, and deleters. Introduction. In this article, we'll explore the at property decorator, a more Pythonic way to use getters and setters in our object-oriented programs. Before we dive in, let's briefly review the concept of getters and setters. Let's recall that getters and setters are useful tools for achieving encapsulation, a way to prevent data from direct modification. We can define a private attribute and then use getters and setters to expose a public means of reading and modifying a class attribute value. Further, getters and setter methods allow us to create complex behavior, such as limiting access under certain conditions or imposing restrictions on allowable ranges of values for an attribute. Let's start by looking at an example class called box with one attribute called weight. In this case, weight will be a private attribute with a getter and a setter, get weight and set weight. We have class box, def init, self weight, self dot double underscore weight is equal to weight. So here we're setting our weight class attribute to private, if I'm correct. Def get weight self return self dot double underscore weight. Def set weight self comma weight if weight is greater than or equal to 0. Self dot double underscore weight is equal to weight. Notice two things. We want to follow best practices by denoting weight as a private attribute using dunder notation. This, however, does not make an attribute private, and we can still manipulate it directly. We are also posing some restrictions on our setter so that the weight of an instance of the box class can only be set to values greater than 0. We can see this if we try to manipulate an instance. Box equals box 10, box.setWeight -5, print box.getWeight, box.setWeight 5 print box.getWeight. That our box weight was unchanged on the first call. So we see 10 and 5. So despite the fact that we ran box.setWeight -5, because -5 is less than 0, and we initialized box with 10, the setter method did not set -5 to be the box's weight. Whereas when we do set weight with 5, because that meets the criteria of a value greater than 0, or I should say greater than or equal to 0, then that actually takes effect. We don't get an error, which is interesting to note. We don't get an error, it just doesn't consider the -5. Notice that we need to call the methods instead of directly interacting with the weight attribute. What if we could have the best of both worlds? That is, a way to directly interact with the weight attribute, but still benefit from the complex behavior of methods, such as the weight restriction. This is where the built-in function property comes in. The built-in property function. The Python built-in property function accepts 4 optional arguments: fget, fset, fdel, and doc. Again, the Python built-in property function accepts 4 optional arguments: fget, fset, fdel, and doc. The first 3 represent getter, setter, and deleter methods respectively, and the last one is a doc string for the attribute. Let's take a look at the advantages by refactoring our box class. So here we have class box, def, dunder, init, self weight, self.dunder weight equals weight, def get weight self, return self.dunder weight, def set weight self, comma weight, if weight is greater than or equal to 0, self.dunder weight equals weight, def del weight self, del self dot dunder weight, weight equals property, get weight, set weight, del weight, doc string for the weight property. Notice we have added one additional method to our class called del weight to serve as a deleter for the property. While it is not strictly required, we will add it to show the full potential of the property function. We then call the property function and pass the getter, setter, and deleter in as arguments. This will immediately allow us to use the following syntax for our class: box equals box 10, print box.weight, this calls.getWeight, box.weight equals 5, this called .setWeight, del box.weight, this calls del weight, box.weight equals -5, box.dunder weight is unchanged. I'm a little bit confused. Oh, sorry. I understand now. With this change, our program gains some immediate benefits. We can now use the weight attribute as if it was public. We no longer have to call the setters, getters, and deleter methods directly, and thus giving our program a simpler syntax. Even though we no longer call the methods directly, we still can maintain constraints, such as the weight limit in set weight. It's the best of both worlds. If we had a huge code base that used our methods multiple times in multiple places, a single change to the method name would seriously mess up our program, since we'd have to change it everywhere. We no longer have this issue using the property method, since we never call it directly. While this is a big advantage for our programs to be more Pythonic, we can go even further by using the decorator pattern to replace the need to call the property function altogether. @property decorator. The most Pythonic way to define getters, setters, and deleters is by using the property decorator. This decorator is syntactic sugar for using the property function and helps our code look much cleaner. Let's take a look. Class box def dunder init self weight self.dunder weight equals weight, @property def weight self, doc string for the weight property, return self.dunder weight, @weight.setter def weight self weight, if weight is greater than or equal to 0, self.dunder weight equals weight, @weight.deleter def weight self del self dot dunder wait. Let's break this down. First, we have renamed all of our methods to simply be wait. Then we denoted our getter with a at property decorator. This marks the property to be used as a prefix for decorating the setter and deleter methods. Lastly, we use at wait.setter and at wait.deleter to define our setter and deleter methods, respectively. This is the equivalent of doing wait equals property get wait, set wait, del wait, docstring for the wait property, and thus giving us the same syntactical advantage as before. Box equals box 10, box.wait equals 5, del box.wait. Wrap up. To summarize, we learned the limitations of using regular setter and getter methods, how to use the property function to create cleaner getters, setters, and deleters. The at property decorator is the most Pythonic way to use the property function. When using the decorator, remember 3 rules. All 3 methods must use the same member name. Example, wait. The first method must be the getter and is defined using at property. The decorators for the setter and deleter are defined by the name of the method at property is used with. Keep the at property decorator in mind when approaching any object-oriented program. It will save time and keep code cleaner and more maintainable. Introduction to exceptions. It is truly an amazing feeling when our code works exactly the way we want it to. On the other hand, it can be equally frustrating when our code runs into errors. Since errors are such an integral part of working with Python, it's important to know how to control errors and use them to our advantage effectively. In this lesson, we will explore a specific type of error, an exception. At this point, we are probably very familiar with the most common type of error, a syntax error. Syntax errors are mistakes in the structure of Python code. They are caught during a special parsing stage before a program is executed. They always prevent the entire program from running. For example, here is the error output of a syntax error. File script.py line 1 defprint 5 syntax error invalid syntax. As opposed to a syntax error, an exception is a different kind of error that can occur with syntactically correct code. Exceptions are runtime errors because they occur during program execution, only when the offending code, the code causing the error, is reached. An example of an exception, and one we have probably seen before, is a name error. Here we see traceback most recent call last, file script.py line 1 in module print 5, name error, name 5 is not defined. Although the name error has a similar output to a syntax error, both end with error, it falls under the category of exceptions. Exceptions and syntax errors make up the 2 core categories for any error we will run into. Python errors fall into category 1 of syntax errors and category 2 of exceptions. We'll encounter many different kinds of exceptions, some of which will be unfamiliar. Luckily, as we saw in the example above, Python gives us a tool for gaining insight into exceptions, the traceback. A traceback is a summary that includes the exception type. A traceback is a summary that includes the exception type, a message, and the series of function calls preceding the exception, along with file names and line numbers. Here's another example of a traceback for a small program. Imaginary file script.py print 1 divided by 0 would output traceback most recent call last, file script.py line 1 in module print 1 divided by 0, 0 division error, division by 0. In the traceback above, reading from the bottom line, we see the exception type 0 division error followed by a message division by 0. Going up, we see that the exception originated on line 1 of a file called script.py while calling print 1 divided by 0. We'll be using tracebacks throughout the rest of the lesson to track and identify why and where our exceptions are occurring. Let's get some practice debugging syntax errors and exceptions. For this lesson, Let's imagine we are hired by Instrument World, a musical instrument company with retail and online stores. Take a look at the code in welcome.py. There is a syntax error on line 3, the extra closing parentheses, right here. Will any of the previous code be executed? Press run to find out. So it'll do print welcome to store equals instrument world, print store. I'm gonna guess no. Fix the error from the extra closing parentheses from line 3. Run the code to see what happens. We hit an exception on line 3 because of the misspelled variable name. However, the previous lines of code were executed. Observe welcome to in the output. Wait, fix the error from the extra closing parentheses from line 3. We hit an exception on line 3 because of the misspelled variable name. However, the previous lines of code were executed. Observe welcome to in the output because exceptions occur at runtime. Fix the variable name on line 3 to continue. Oh, okay, so if I did this, I think I skipped too far ahead. The point was to show me. I don't understand what they're trying to say. Fix the error from the extra closing parentheses from line 3. Run the code to see what happens. We hit an exception on line 3 because of the misspelled variable name. However, the previous lines of code were executed. I don't know what they mean. Because exceptions occur at runtime. Alright, I'm a little bit confused. Built-in exceptions. In the previous exercise, and probably many times before, we saw one type of exception called the name error. The name error is just one of the many built-in exceptions that are built into the Python language. Other built-in exceptions cover fields ranging from mathematical errors all the way to operating system errors. We don't need to memorize them all, but it's helpful to be familiar with some common ones and, more importantly, understand where they come from inside Python. Exceptions are objects just like anything else. Most exceptions inherit directly from a class called exception. However, they all are derived directly or indirectly from the base exception class. We can examine the base classes by using the dunder bases dunder attribute on any specific exception. Print name error dot dunder bases dunder will output class exception. We can even call dunder bases dunder on the exception class to see its origins. Print exception dot dunder bases dunder will output class base exception. The full hierarchy of built-in exceptions is the following. As you can see, it all starts with base exception, and then within that is exception. And there's many different types of exceptions and errors that are within that exception class. Note that there are a lot of exceptions built into the language of Python. Again, we don't need to memorize all of them, but at some point, we may see them pop up in our programs. We can find details on each of the exceptions listed above in the Python documentation. Later in this lesson, we'll be using the exception base class to create custom exceptions. For now, let's get some practice encountering built-in exceptions and reading their tracebacks. Instrument World has a program that prints some of the most popular instruments it has on sale. Take some time to look over the program and then run the code in instruments.py. We'll encounter another exception that we might not have seen before. What might this exception be telling us? So sale instruments is a list of violin, conga, clavinet. Print the following plus length of sale instruments, which would be 3, which needs to be wrapped in string. Plus instruments are on sale. Print sale instruments 0, print sale instruments 1, and print sale instruments 3. So this is index error, and this is a type error. Type error must be string, not int. Take a look over traceback. It ends with the exception type and a brief message. Above that is the exact line that caused the exception. Fix this line so that the exception no longer occurs, and then rerun the code. Looks like the exception we saw in the previous step was a type error. Let's confirm which base class it is derived from. Use print to output a type error basis. I should have known. And I did know. But I should have known. Type error. Bases, class exception. There's another exception that gets hit once again. Read the traceback, fix the exception, and rerun the code. We have an index error, list out of range. Nice. Raising exceptions. Encountering exceptions isn't always an accident. We can throw an exception at any time by using the raise keyword, even when Python would not normally allow it. We might want to raise an exception anytime we think a mistake has or will occur in our program. This lets us stop program execution immediately and provide a useful error message instead of allowing mistakes to occur that may be difficult to diagnose at a later point. One way to use the raise keyword is by pairing it with a specific exception class name. We can either call the class by itself or call a constructor and provide a specific error message. So for example, we could do raise name error or raise name error custom message. And again, we might want to raise an exception anytime we think a mistake has or will occur in our program. This lets us stop program execution immediately and provide a useful error message instead of allowing mistakes to occur that may be difficult to diagnose at a later point. Okay. When only the class name is provided, as in the first example, Python calls the constructor method for us without any arguments, and thus no custom message will come up. For a more concrete example, let's examine raising a type error for a function that checks if an employee tries to open the cash register but does not have the correct access. Def open register employee status. If employee status is equal to authorized, print successfully opened cash register. Else, alternatives raise type error or type error message. Raise type error. When an employee status is not authorized, the function open register will throw a type error and stop program execution. Alternatively, when no built-in exception makes sense for the type of error our program might experience, it might be better to use a generic exception with a specific message. This is where we can use the base exception class and provide a single argument that serves as the error message. Let's modify the previous example, this time raising an exception object with a message. Def open register employee status. If employee status is equal to authorized, print successfully opened cash register. Else, raise exception employee does not have access. As a general rule of thumb, use an exception that provides the best explanation for the expected error for both the user and anyone that will read the code. Later in this lesson, we'll explore how to customize our exceptions further by creating user-defined exceptions. For now, let's practice using the raise keyword. Instrument World has a program that attempts to print the price of several instruments. Take some time to examine the program and then run the code and observe the output. What do we expect to happen? So instrument catalog is a dictionary, marimba, $1999, kora, $499, flute, $899. Def print instrument price, takes in an instrument argument, write your code below. Print the price of a plus instrument is string instrument catalog instrument. So instrument catalog instrument. So if we do print instrument price marimba, then we get the price of a marimba is instrument catalog marimba $19.99. We're converting it to a string. So Instrument World has a program that is to print the price of several instruments. Take some time to examine the program and then run the code and observe the output. What do we expect to happen? Should work, right? Oops. Oh, I didn't notice that piano isn't in here. Key error, piano. We had a key error since piano was not a key in the instrument catalog dictionary. Let's provide a custom message by raising the exception ourselves. To accomplish this goal, we'll use a simple conditional. First, inside of print instrument price, add an if statement that checks whether or not the instrument parameter is found in instrument catalog. If it is, use the provided pre-written print statement to print the price. So if sorry, my apologies. So if instrument in instrument catalog, print this. We'll do else pass Finally, let's add an else block where we will print our custom key error exception if the key does not exist. Inside, it should raise a key error, so raise key error with the message instrument plus is not found in instrument catalog. Traceback, key error, piano is not found in instrument catalog. Nice. Try except. So far, the exceptions we've encountered have caused our programs to stop executing. However, it is possible for programs to continue executing even after encountering an exception. This process is known as exception handling and is accomplished using the Python try except clauses. The following flowchart demonstrates the mechanics of try except. Start, execute try clause. Exception encountered, no, then end. Exception encountered, yes, execute except clause, then end. Let's break it down. Python will first attempt to execute code inside the try clause code block. If no exception is encountered in the code, the except clause is skipped and the program continues normally. If an exception does occur inside of the try code block, Python will immediately stop executing the code and begin executing the code inside the except code block, sometimes called a handler. Let's see this in action in a small program that prints colors. Colors equals red, that hex value, blue, that hex value, and yellow, that hex value. For color in red, green, yellow, try print the hex value of plus color plus is plus color's color, except print an exception occurred, color does not exist, print loop continues. We'll get the following output. The hex value of red is that, loop continues, an exception occurred, color does not exist, loop continues. The hex value of yellow is that, loop continues. In the above code, the try block runs until it hit an exception. The hex value of the color red was successfully printed before it tried to access the hex value of green, which caused a key error since green is not in our colors dictionary, and ran the code in the except block. However, the exception was handled, so Python continued executing our code and went on to print the hex value of yellow. Exception handling is a powerful tool that lets us gain more flexibility in dealing with errors in our applications. We can use it to perform an action multiple times until it succeeds, or perhaps simply print a message when a non-critical part of our program doesn't work properly. Let's try performing some exception handling. Instrument World has a program that prints a staff report for all of the Instrument World locations in the staff dictionary. Take some time to review the code. Spot any issues? So staff is a dictionary with a key Austin and a dictionary floor managers 1, sales associates. Sorry, give me 1 second. Oh no. Alright, I gotta go.